a change in the team of this seminar. So Dominic is still on board, of course, but today, unfortunately, he cannot join us. Nizark is also on board and unfortunately cannot join us either, but the rest of us is here. So that's Florian and Anaël and myself, and I would chair the session today. And I'm very happy that we have an all Oxford seminar today with Sonja Kraiczy and Tomasz Vance. I hope I did a good job in pronouncing that. So since I do not see, oh yes, I see one person in the waiting room, but now I think no one else in the waiting room. Okay, two more. Let's wait 1 minute and then start with Sonja, who will present work on hedonic coalition formation, right?
Random.
So,
yeah.
Yes. Okay. All right, Sonja. So maybe you want to share the screen. All right. The format is as usual. There's 20 minutes of presentation, 10 minutes of questions and answer. Then there is a 10-minute break. We all go in breakout rooms and chat for 10 minutes. And then the second talk for 20 minutes again and 10 minutes Q&A. All right. So floor is yours. Please, Sonja.
Okay, hi everyone. So yeah, today I'll talk about stability in random hedonic games, and this is joint work with Martin, who I believe is also in the audience, so he'll be able and help me answer questions later. And yeah, this is also work that I presented at EC like roughly 2 months ago. So let's get started. And what is the setting? So we're in a cooperative game theory setting, and we have agents which we want to partition into coalitions. So we don't just care about any old sets. It's cooperative game theory, so we care about some desirable stability properties of these coalition structures. And because we're computer scientists, we also care about algorithms to achieve them efficiently, right? So the questions are all kind of, how do we obtain desirable coalition structures algorithmically? And so let's dive into the formal model that we consider. So that is that of hedonic games with additive utilities. So a hedonic game with additive utilities is just a tuple, which consists of the capital N, the set of little n agents, and U, which is a tuple of utility functions. So each agent is associated with their own utility function, and this utility function assigns to every agent a utility. And the convention is that an agent has utility 0 for herself. So where does the additive part come in? So an agent evaluates a coalition, which is just a subset of the agents, by taking the sum over the utilities of the agents in that coalition. And then we can talk about preferring coalitions. So an agent will prefer or weakly prefer coalition C to C prime if she has high utility for C to C prime, and similarly will strongly prefer, has strictly larger utility. And as I said already, the goal is kind of to partition the agents into these coalitions, and then every agent can afterwards evaluate the utility for their own coalition, the utility for other coalitions, and so on. So let's consider an example. Here we have 5 agents, and the bear, the mouse, and the hippo are in their own coalition, and the owl and penguin are in the second coalition. And then the directed error, so an edge from I to J, is labeled with the utility that agent I has for agent J. And if the edge is missing, that just means 0 utility. And so next to the agent is the utility that the agent has for their current coalition. So the bear has -6 because it has -6 utility for the hippo and 0 for the mouse. But the bear also has utility 5 for the other coalition because it has 5 for the owl and 0 for the penguin, meaning the agent strictly prefers the other coalition to his own coalition. And so this leads us directly to notions of single agent stability. So this bear is performing or wants to perform a Nash deviation because it has a beneficial deviation to this other coalition. And then we say that a partition or a coalition structure is Nash stable if there's just simply no Nash deviation. So there's no agent who has a beneficial deviation to another coalition. Similarly, we say that a coalition structure is individually stable if every Nash deviation is blocked by an agent in the coalition the agent wants to join. So in this case, while the bear wants to join, and even the penguin is fine with him joining because he has utility 0 for the bear, so he doesn't care, the owl has utility -1. So generally, an agent will block another agent from joining if they have negative utility for that agent. Finally, a coalition structure is contractually Nash stable if every Nash deviation is blocked by an agent in the coalition that you're trying to leave. So the bear is trying to leave the coalition with the hippo and the mouse, but both of them actually have positive utility for the bear. So they would block bear from leaving. So in general, you will block an agent from leaving if you want them to stay, right? You have positive utility for them. So now we have these 3 single agent stability notions, and the latter 2 are weaker. So they allow for some Nash deviations to exist, but with the caveat that we say, well, they exist, but they kind of, something will prevent them from happening in practice because the agents in the coalition that they want to deviate to will block, or they want to, the coalition they want to leave will block. And so let's consider the existence of these notions, and let's consider the strongest one, so Nash stability. And a very simple example shows that Nash stability cannot be guaranteed in general. So consider Tom and Jerry. And Tom wants to be in a coalition with Jerry. Tom has positive utility for Jerry, but Jerry has negative utility for Tom, right? So there's 2 options. There's the grand coalition and the singleton coalitions. Tom wants to be in the grand coalition. Jerry does not. Jerry wants to be in the singleton coalitions. So clearly none of these 2 coalitions is Nash stable. And this run and chase instance kind of shows that Nash stability is just too demanding because we have such an easy example. So maybe this is just too strong, and maybe the other notions that are a bit weaker would be better. Now, there may not be as simple counterexamples, but there are slightly more complex examples that show that even for these other 2 notions of IS and CNS, they are not always satisfiable. Okay. And the bad news continues. So there's been work studying the complexity of these, because it's a very natural question to at least be able to see when it exists and when it doesn't exist. And if it does exist, can we find it? All of this efficiently, of course. And so the bad news is that for each of these stability notion, it is NP-complete to decide if there exists a partition satisfying it. And that's why in this work, we set out to take a different approach, and we sort of asked ourselves, when you have many, many agents, do we typically expect stable coalition structures to exist? So for example, with high probability, what about stability in random games? And so the first thing, the first conceptual contribution is that we have is introducing this very, I think, natural model of random hedonic games. So the random hedonic game model H of n, curly d is going to be a distribution over additive hedonic games. And n is just the parameter which will be the number of agents, while curly d gives you the parameter which is the probability distribution over reals and will give you the distribution from which we sample utilities. In particular, the tuple n, u will be sampled from this random hedonic game model by just taking n to be the set of little n agents. And for every 2 distinct agents, I and j, the utility of agent I for j is sampled IID, so independently and identically from this distribution curly d. And then this will be the notation for how we sample from this random game model. And in our work, because it's quite complex to analyze this, and already in the impartial culture setting, it is complex. So we focus on the impartial culture assumption, which means that the distribution is the symmetric uniform distribution. Okay. And And so the kinds of questions we are interested now, so consider some desirable property curly P, that may be stability and will be in our case. And now we want to say, so when we sample a random game from our random hedonic game model, what is the probability that it satisfies this desirable property? And in particular, how does this probability behave in the large agent limit? So as the number of agent grows. Is it 1? Is it 0? Is it some constant in between, right? So I will omit this underscript for the sampling, and whenever you see this, so n comma u satisfy this, it means that n comma u is actually being sampled from the random hedonic game model, where the distribution under consideration is the symmetric uniform distribution. And then if we do find a positive result for this probability, well, as I said before, we also care about efficient algorithms. So ideally, we'd also want an efficient algorithm that efficient in terms of n, the number of agents, that then with high probability returns a partition that satisfies the property of interest in the large agent limit. Right. And so I already introduced these three stability notions. Though they were NS, IS, and CNS, so Nash stability, individual stability, and contractual Nash stability. And so we set out to answer these three questions. So what are these limits, right? Like, do they exist or do they not exist? Or with what probability do they exist in the large agent limit? And so we managed to answer all of these questions, and these are the answers. So Nash stability is really hard, really challenging, even as n grows large, while the other two we can satisfy with probability 1 in the limit. And as I said, it's not enough to just have a positive result. We also want an efficient algorithm. And so that's what I will focus on for the rest of the talk. So I will just say, so 1 is our main negative result, 2 and 3 is our main positive result, which I will focus on. But I will say that our main negative result is probably as or more challenging technically. So the proof is rather long or longer than this one. But let's go to the main positive result. And as I said, we find an efficient algorithm, so an algorithm that is polynomial in n, that outputs a partition that is both individually stable and contractually Nash stable if the input is a random hedonic game. Now, another thing that I think is desirable in our algorithm satisfies is not just to give any old partition. So there's certain partitions that seem less desirable, like the grand coalition. If you have many, many agents, that seems unfeasible, or singletons seems not very desirable. So, and these both seem impracticable due to their coalition sizes. And also we wouldn't really like asymmetric partitions. So what is nice about it, that it outputs actually balanced partitions, which means that the coalition sizes will differ by at most 1. And actually the coalition will have size beta log n. So not too large and not too small, roughly, I think, a nice size. And this algorithm that we give actually satisfies slightly stronger condition than individual stability and contractual Nash stability, namely these three. And these three together imply the other two. So the three are individual rationality, which just means every agent should have non-negative utility for their own coalition. Entry denial, so an agent is denied entry in all other coalitions. And note that here, it doesn't matter whether they actually want to deviate to that coalition, well, they will be denied anyway. And exit denial, so whether agent wants to leave or not, they will be denied from leaving the own coalition. And so clearly exit denial is stronger than contractual Nash stability, and then entry denial and individual rationality together imply individual stability. So these exit and entry denial properties just don't even care whether there's Nash deviations, right? Whether they're there or not, we will be blocking the deviations, potential ones. And so we can restate this result saying that this algorithm actually outputs our partition satisfying all of these three properties at once. And so let me say more about this algorithm. Namely, it consists of 3 stages. And in stage 1, the key basis of stage 1 is a result from random graph theory. So this random graph coloring algorithm by Grimmett and McDiarmid is what we use. And stage, basically these 3 stages play different roles. So we try in these different stages to satisfy these 3 properties, but there's no kind of one-to-one correspondence. And I will mention briefly how they correspond later. But let's first go into this stage 1 of the 3 stages. So the goal is to form initial coalitions that are quite of nice quality. So agents will have quite high mutual utility for each other. In particular, kind of every agent pairs will all like each other in these coalitions. And the algorithm by Grimmett and McDiarmid works roughly as follows. So consider this orange agent, and we just initialize a coalition with the orange agent. And then we consider the green agent. And we want them to mutually like each other. And we just arbitrarily kind of define this positive threshold of a half and say green can join if they both like each other, right? And so green joins. And now for gray, both green and gray and orange and gray have to like each other. And for green, that's the case, but for orange, not. So gray is rejected. Now, blue actually is going to be added. And so you keep going and eventually you can't add anyone. And then what the algorithm does is you recurse on the set of the remaining agents n. And we adapt this algorithm because we want all of our coalitions after stage 1 to have exactly equal size. So we slightly change this algorithm and also change parameters. So it's originally for random graphs, right? And then we get after the stage 1 that the following. We get that with high probability, right? Meaning tending to 1 as n tends to infinity. All except at most n over roughly log squared agents are assigned to coalitions of size of the order of log n. So note that if you subtract from n the number of remaining agents and divide by the coalition size, you will see that we have of the order of n over log n coalitions. So that's an order of magnitude larger than the number of remaining agents. So it's actually not that many remaining agents that we still have to deal with. And so what is nice is that we have these good quality coalitions now. So individual rationality is satisfied. And also, obviously, exit denial is satisfied for agents in those coalitions because everyone likes each other. So it's actually quite strong exit denial. But unfortunately, we fail entry denial. So the coalitions are too small. And even if you take sort of optimal results from random graph theory, sort of the maximum clique that exists with high probability, even those sizes, when we try, they're not big enough to guarantee entry denial. So we really kind of have to give up the idea that these coalitions will be as high quality, and we will need to water them down a little bit. So you can think of the coalitions will consist of your best friends, your kind of clique, and then we will add some acquaintances. But overall, the quality will be slightly worse, but not too bad. And so this was what we do in stage 2. And the goal is to make the coalition right larger, so that it's very likely that for any given agent, someone in this larger coalition is going to reject them. So I will not go into the details, but the stage 2 roughly does this, right? So we find some way to increase these coalitions so that now they are large enough. And actually, like a constant factor, a sufficiently large constant factor larger is enough. We again have some leftover agents that we need to deal with, but now we have successfully enlarged these coalitions, and we will be able to guarantee entry denial even for the remainder agent, also for the other agent. It's just large enough for the analysis now. And then finally, in step 3, we have to do cleanup because we have all these remainder agent rights, and we need to make sure that they're assigned to coalitions for which they have non-negative utility. We need to make sure that exit denial is satisfied. So then we have a stage 3 that takes care of that. So in summary, we have these 3 stages. And in stage 1, we take care of individual rationality initially, or that is, it is also later than having done again in the stage 3. Stage 2 takes care of both entry and exit denial. And then stage 3, as I said, when we deal with the remainder agent, we mainly are worried about individual rationality and exit denial. So in summary, let me remind you of what I told you. So we introduced a random model of hedonic games, and we started a high probability analysis in the large agent limit. And we have two main results. One is a negative result, so that even in this random setting, the probability that Nash-stable coalitions exist tends to 0 as n tends to infinity. But we gave an efficient algorithm that returns coalition structures that are both individually stable and contractually Nash stable. And furthermore, they kind of give nice coalition structures. So they're balanced. Coalitions have roughly equal size, and they're of order log n. So if, I don't know, n is 10,000, they're not too big. And so, yeah, that's what we did. And I think there's a lot of interesting future work. So one can look at more general distributions, obviously, and other properties. I think it's interesting to consider correlated preferences. So, for example, agents have global popularity, how much you like other agents. If an agent is very good, will be correlated, or maybe pairwise preferences between agents will be correlated. And perhaps that will help with Nash stability. And otherwise, you might want to simultaneously satisfy both stability, but also approximations of global measures, such as social welfare, or there's other optimality criteria that kind of come from the correlation clustering and community detection communities, which one might simultaneously want to satisfy. And yeah, that's everything.
All right, so thanks very much. Let's applaud for the talk. Very nice. There have been already questions in the chat, but I may take the liberty to ask a question of understanding first before we go to these more detailed questions. I have one general question about the methodology. So you depart from the usual fixed number of individual deterministic case in two ways at the same time, right? You introduce randomness and you do large N analysis. So my question is, why do you do that? Wouldn't it be so my natural way to solve these problems would be to try to calculate the probability of some properties for a fixed N. And then automatically, when you then ask, well, how does this probability change with N, you could simply see it in the formulas. But I suppose there is a reason why you cannot do this here. Do you understand my question?
I mean, we have like it's also a bit for presentation. Like if I give you like, oh, it's probably 1 minus 2 to the n log n times log n times some constant. So usually, so the way the probability decays is going to be like 1 minus something that's decays to 0 faster than like a polynomial. It's going to be like super polynomial usually. But like exactly calculating is exactly, it's just too hard. I mean, these are like bounds, right? These are not like they're not tight, I guess.
I see. So you
I would say just too difficult.
Yes, for a fixed N, you have bounds for the probabilities, and then you can say something about the asymptotic behavior of the bounds.
Yeah, and that is even like grows, like tends to 0. These errors tends to 0 faster than like inverse polynomials.
Okay, very good. Then Bill had a question, exactly what you also suggested in your future directions about more general distribution. So he asked the question, do you need the symmetric uniform distribution? How robust are the results? And I think Martin already answered this. Martin, do you want to add something there?
Yeah, sure. I mean, I can. So what I can maybe just say what I answered to Bill, and then Sonja might want to add, because she is actually also investigating exactly this question, or we are investigating this. So generally, I think to make the presentation nice and so on, in our algorithm, we assumed the -1,1 uniform distribution, because there are various parameters that you set to certain constants and so on. But really, these parameters all depend on the distribution, and you have a lot of freedom to choose these, and then you can actually extend the algorithm to larger classes of distributions. And yeah, maybe Sonja wants to add on what classes of distributions and so on, because I mean, I could give the answer, but I won't.
Yeah, so I think even when we were writing this, we were thinking of doing more general distributions. It's just that the details are really, really fiddly already. And then we underestimated how many details. We think it's probably can effects, but at many, many different positions, you have to slightly change something or be careful about changing things. But we generally believe that, so maybe something to consider is still mean zero symmetric distributions, but maybe sub-Gaussian distribution. So tails that decay like at least as fast as Gaussians, for example. So Gaussian would be a particular example of that. I think for those, it'll probably still be true. You have to use slightly different tail bounds and be a bit more careful because you don't have this for sure cutoff beyond a certain bound, right? So it's going to be even more probabilistic analysis, but I think those, I'm pretty confident those hopefully can be satisfied. For non-mean zero, it's not as clear. For example, one interesting thing is if you consider a distribution with positive mean, and you consider the Grand coalition, then because of the arguments of like the central limit theorem, you can argue that everyone with high probability will have positive utility for this coalition, and so no one will want to deviate. Now imagine even you have a distribution that's uniform over 0, 1, right? So always positive. Then we know that the Grand coalition is Nash stable, even so quite strong, but is there any other coalition structure that is going to be Nash stable? Is that the unique one? So there's like other interesting questions like these if you go beyond mean zero distributions.
Okay. Andrei Kostin, your question has been answered already, or is there something to add? Okay. Yeah. So then Peter has a question. Peter has a question. What happens if the negative utilities are correlated? So some agents are hated by everybody. Can you say something, Sonja, on that case?
So if,
or perhaps Peter can be a bit more precise. What is the intuition that you have perhaps here?
My intuition is that agents who are hated by everybody will form a singleton coalition because no one wants to cooperate with them. But the algorithm was guaranteed to give coalitions of a minimal size. So where does that break down?
So the algorithm will not the algorithm will not work for correlations, I guess. It'll have to, like, I have to think about if it can be adapted, but if your question asking if your question is if the algorithm still works, I guess probably not. Or what is the...
Yeah. Yeah, it makes sense, right? I mean, what Peter just said, if these people are hated by everybody, so they must form coalitions by themselves, right? So it seems to make sense.
I mean, not quite, right? Like if you have, so it's not completely clear because it's fine if there's few agents, right? Like we have n over log n coalitions, right? Let's say there's much fewer than that coalition agents hated by everyone. If otherwise you have enough positive people who are canceling out that effect, then you might be fine with having someone you don't like in your coalition, as long as your overall positive utility is high enough, right?
But I still think such an agent would be kicked out, according to your criteria.
I mean, yes, if you really have everyone hate them. I mean, the criteria here, I guess, are about the notions of deviations right now are not about kicking out. They're about whether an agent themselves, right? They're their own coalition and other coalitions, and they choose themselves. Do they want to stay or leave? It's not about whether people in that coalition are kicking them out. It's about, do they allow them leaving or do they not allow them leaving? Or do they allow someone enter or do they not allow someone to enter?
Okay. Now, good luck with your project.
Maybe if
All
I
right.
can add on the
Yes.
subject of
Yes,
correlation.
of course. Yes, please.
But maybe a general, so certainly if you have other model assumptions, you will have to adapt the algorithms, but our general intuition is probably that correlations only help in facilitating stability. So if you have correlations, then achieving stability should be an easier task. So you can make this more rigorous in some way by looking at models that have correlation, but so generally I would say like these notions that we want to achieve with our algorithm, like these every agent has non-zero utility, and then this V2 out and V2 in properties, if we have correlations, they are easier. They tend to be easier to achieve. Yeah. But working out the details in a random model where you incorporate correlations is definitely a more advanced task.
All right, let's move on to the next question. Andre again asked a technical question. Can you come up with a non-pathological, say, continuous distributions D where the limits don't tend to 0 or 1 in your, I assume in your theorems?
Yeah, because like you get that sometimes it converges to 0, sometimes to 1. Of course, if you fix an n, it will convert to some random number, but in the limit, it will tend to 0 or to 1. So I wonder if there really exists any time when the limit will converge to something weird. Like I don't know, it just tinkles my mind a bit.
I feel like, I mean, I just feel like so my intuition is that a better way to try to achieve like a constant probability is try to think of maybe of different stability notions instead, because it's quite a big contrast between Nash stability and those other ones. In Nash stability, it's really just whether you deviate, while in those other notions, it's just enough if one person, one agent in the other coalition, one agent in your coalition, and sort of satisfying that is not that hard. So I don't know the answer, but I was thinking at some point with regard to correlation, what would be really nice, like whether you can have some, so we have completely uncorrelated, right? So correlation is 0 here and independent, and we have a probability of 0 for Nash stability. And as you increase correlation, can you have like, is there going to be a phase transition in the probability of satisfying Nash stability? Like, is it going to be suddenly going from 0 to 1, or is it continuous? Is it like a function of this whatever parameter you have? So I don't know the answer, but we're interested in related questions to that, whether there's kind of like in between probabilities.
But even for okay, I mean, for correlated, there might be a way to make it tend to something else, just because you can correlate it in a weird way. If you don't correlate, there is actually a chance that for every D that is sufficiently well behaved, it tends to 0 or 1. That would be a cool thing to prove. Somewhat,
we were discussing with Martin, there are these like results from probability theory of like certain kinds of events that can only probabilities that can only be either 0 or 1. So it would be interesting. Like Kolmogorov or something has results like this. So it would be interesting to look at that next.
All right. So then we have that's a good point to end the discussion, that there is interesting things to do still. So thanks a lot. I think we have reached the time limit also for the question and answer. So let's go to the breakout room and welcome back to the second session of today. So the speaker will Tomasz Vance on the method of equal shares with bounded overspending. And I'm sure Tomasz will explain us what bounded overspending is. So Tomasz, the floor is yours.
Thank you. So yes, this is a joint work with Georgios, Zane, Oscar, and Piotr, and I think all of them are in the audience also. So if you have any questions, they should be able to answer them on chat. And yeah, my talk will be about participatory budgeting. So this is the process in which typically cities, but also other organizations decide upon some parts of their budget through the means of direct democracy. So the citizens express their preferences over the number of projects, and then usually through voting, and then we use some voting rule to decide which projects we will actually fund and implement in the end. So I'll be talking about 3 rules for such process, and the first one will be utilitarian greedy method, which is currently the most commonly used method for participatory budgeting, and it's actually very bad. The second method, which is much better, it's called method of equal shares, and it was recently proposed, and it's already used in some of the cities, and it's much better, but unfortunately also has some problems. I will be discussing them. And finally, I will be also talking about method of equal shares with bounded overspending, which is a new rule for participatory budgeting that we are introducing in this work. Finally, I will also do some kind of comparison on real-world data, how do they perform. So let me start by saying more formally what I mean by participatory budgeting instance. So here we will have some number of projects like athletic gym, basketball courts, or like dinosaur park. And each of these projects is associated with some fixed cost. So for example, athletic gym costs 300. So this means that in order to implement athletic gym, we have to pay this 300. Then we have voters, and voters will have some preferences over the projects, which in our paper, we assume that they are arbitrary utilities. We only kind of say that they are additive. So, but for the purpose of this presentation, I will only consider preferences that can be specified using approval voting, and I will assume so-called cost utilities. So I will say that if, for example, voter 1 approves project A, then this means that if the project A is selected, this voter will get utility 300. And this is a very common assumption in the literature, and it also makes intuitive sense because the projects that are more expensive, we kind of assume that they are of the larger scale. So it makes sense to say that the voter will be more happy if such a project is selected, implemented, not some like very cheap one, instead of some very cheap one. Yes, and the final ingredient of our participatory budgeting instance is a budget, which is also some fixed number. And then the goal is to select some subset of projects in such a way that their summed costs do not exceed the budget. So how we can do it? Well, we can use, for example, the utilitarian greedy method, which is the most commonly used method nowadays. And the method works like this, that we look at our projects from the most approved to the least approved. Fortunately, they are already in this order here. And then we look at the highest on the list project that we can still afford. So this will be project A, for example, here, because it costs 300 and we can afford that. And then we buy it, we update the budget, and we repeat the process until we run out of money. So as you can, it's very easy to see that in this case, we will just select project A, B, and C. And now we can look how happy are the voters from such a selection. So we can see that actually some voters are extremely happy because we spent the whole budget on the things that they liked. But at the same time, some other voters are very unhappy because they didn't receive anything that they liked. And this is very bad because this is like large part of the voters that are unsatisfied. So we can say that's unfair, unproportional, and this is generally what we don't want. So how we can avoid that? So we can avoid that by using this method of equal shares, which was designed specifically for this purpose to make the selection more proportional. So one of the main changes between this rule and the previous one is that instead of just having one central budget for everyone, we now split this budget into equal parts between the voters. So each voter has this 100. We don't really give them money. We just kind of put the variable in our algorithm. And now when we want to select some project, like project A, then we will expect that the money for this project will actually come from the budgets of these individual voters that support this project. So these are supporters. So for example, if we may want to make this spread these payments as equal as possible. So for example, if this project costs 300, then we want every one of the 6 supporters to just pay 50 out of their budgets. And now to compare which project actually we want to select out of all projects, we look at something that is called RAW, which is how much the ratio of how much they are paying for each unit of utility. And actually, when we have approval votes with this cost utilities, this RAW also has much simpler meaning. It's just the fraction of the whole payment that a given voter is making. Yes, so for example, the first voter is paying 50 out of the total 300, so it's 1/6 of the total payment. And then we look at the maximal RAW out of all this RAW of the voters, which is the worst one. Yes, because the RAW is like how much we pay per utility. So the smaller this number, it means that we pay less for utility, the same utility. So we want to have it like as small as possible. So this max RAW is kind of the worst one for this project. And then we are selecting a project in order to minimize this maximal RAW. Yes, so it's kind of like a min-max RAW. And for example, in here you can see that we will not be able to, for any other projects, we will not be able to get better than 1/6 because no other project is supported by 6 voters. So we will not be able to get a better kind of this ratio. So this is why we are selecting the first project A, and then we are updating the budgets of the voters. They just pay for this project, and then we proceed the same way. So in the first round, we selected project A, and now in the second round, things get a bit more interesting because, for example, we can see that we can no longer afford project B. Because the voters, the supporters of this project, for the voters 2, 3, 4, 5, and 6, they only have 50 each. And in order to cover this 400, they would have to pay 80. So that's too much. And we know that actually during this process, they will not get more money. So we know that we will never actually buy this project now anymore. And we can just cross it out from the list. Next, we can look at the project C. And now we see that, okay, if we split this money equally, we also cannot do this because we cannot say that we cannot make everybody pay 60 because 4 of the supporters of this project they only have 50. However, what we can do and what we actually is doing the equal shares is saying that okay, but maybe the last voter that still have like a full budget, maybe this voter can pay for the other ones. And this is possible. We could still afford this project in this way. However, what we can observe is now that this voter, the 10th voter, will pay 1/3 of the whole payment. So its RAW will be 1/3, which is much larger than for example, 1/4 that we would have for the project D, where we have 4 voters, 4 supporters, so less supporters, but we can spread this money, these payments equally between them, and then we will get this RAW of 1/4 for each of them. So equal shares prefers like an equal spread of these payments. And this is actually the best RAW we can get in this round. So this is why we are selecting project D. We are buying it, updating the budgets, and we proceed in this way. And the final selection will be A, D, and E. And now we can look at the happiness of the voters, and we can see that we have much more uniform spread, which is exactly what we wanted of this happiness. It's much more uniform, what we wanted. So that's very nice. We can also prove that method of equal shares satisfies EGR up to 1 axiom, which is very strong proportionality axiom. So this is also good. However, as I mentioned at the beginning, it also has some problems. And one maybe you can see already is that actually the money that is left for the voters, it sums up to 290, which is quite a lot. In particular, it's more than, for example, the cost of this project F. However, because the voters that support this project, they don't have enough money, method of equal shares is not buying it. And we say that equal shares is not non-exhaustive, and this is actually quite a problem because it happens quite a lot in real life, and so there are different completion methods that were proposed to deal with this problem, but they also have their problems, so it's not very nice. But I think what is even more important problem of method of equal shares is what we call Helenka paradox. So what you can see here is the real-world instance of participatory budgeting from 2020 from district of Helenka in Polish city of Zabrze. And here 2 projects were proposed. So it's a small district, so only 2 projects were proposed. One of them is sport facilities, and it costs 310,000, which is the whole budget that we have. And it's supported by like a vast majority of voters, 97%, but not all of them, which is important. On the other hand, we have the second project, which is plant sculpture. It costs 6,000, and there are 11 voters that like this project. So now what method of equal shares would do for such an instance? First, it will look at the first project, and you can see that because it costs the whole budget, but not all of the voters support it, then for every voter, when we look how much they would have to pay, it will be tiny bit more than what they have. So actually, it turns out that we cannot afford this project, and equal shares will not select it. On the other hand, when we look at the other project, then the budget, this very small cost actually fits into the budgets of these few voters, and we can select it. So this is what will be the output of the method of equal shares. And now it will make some voters happy, but vast majority will be very unhappy. And you can see that this output is actually proportional. Yes, like for example, EJR would tell you that this should be the outcome in this instance. Like if you want to have a rule that satisfies EJR, you would have to select this. However, you can like proportionality very much, but it makes a lot of voters unhappy. Yes? And at the end, it's voters that decide what rule we are using. So if the voters would not like the output of the rule, probably they will not also like to use this rule. So I think we really need to fix it somehow. And one of the fix is exactly the method of equal shares with bounded overspending that I will introduce now. So it works very much similar to standard equal shares. However, sometimes we allow the voters to spend more of their budgets than what they have. And if we are doing something like this, then we will kind of put some penalty on this row by which we are proposing by which we are comparing the projects, and this penalty will be higher if if they have to overspend more of their budget. So I will explain it in detail in the example in a moment. Let's just first say that in the first round, bounded overspending, or like BOS in short, will select exactly the same as equal shares, so the project A. Now in the second round, the things will get interesting. So for example, maybe you remember that for method of equal shares, we were not buying this project B because the supporters didn't have enough money. But now for BOS, we are able, like we said that we sometimes allow we can allow for the voters to spend more than they have. So we can say that, okay, maybe they can spend each of them 80, that it will be more than what they have. And this will actually give us a row of 1/5. However, we can say that if we allow for that, then in real, with their real money, they will be only able to cover 5/8 of the total payment. So what we are doing is now we're taking this row that we have, the max row 1/5, and we divide it by the fraction that they can afford. So the greater the fraction, the smaller the fraction, the more kind of hurtful it will be on the row. So here we will end up with row 8/25, which is greater than 1/5, so it's worse. However, it's still not so bad. For example, when we compare it to this row of 1/3 that we have for project C, it's better than that. Yes, 8/25 is actually smaller than 1/3, so that's better. However, for project C, we can also kind of allow for overspending and see what will happen if we spread the payments equally. then the row will be 1/5, so it's much better. And also we are able to cover large part of this project, yes, 5/6 with such payments. So we divide 1/5 over by 5/6, and we get 6/25, which is better than 1/3, and which is better than 8/25. And actually, it's better also what we would get for project D, E, and F. So BOSS selects project C and updates the budget. So some of the voters now go below 0, and we are treating them as just as if they would have 0 money from now. So they will not have a say what will come next in the algorithm. And we proceed this way, and actually what we'll end up having is project A, C, D, and F. And the utilities are also kind of well spread out, with the exception that for some voters actually they are higher, which means that overall utility is higher, which is promising. We like by design, BOSS is not meant to satisfy EGR because we don't want to satisfy it, for example, for Halenka paradox, but it's still good to know that it satisfies some EGR approximation. So that's also nice. Now with BOSS, we can actually solve Halenka paradox because what we just simply can do is we allow this large amount of voters to overspend by a bit. And this will give us like much better ratio than for the other project. So this will be we for BOSS will select the first project, and that will solve our issue. Okay, so let's see how actually these rules will now perform in practice in some more kind of comprehensive study. So what we did is we looked at all participatory budgeting instance on public library, and there are like almost 1,000 of them, and they come from like real world. They are real world instances, most of them, and we have compared the outputs of the rules on different statistics. And we observed that they behave a bit differently on different sizes of instances. So we spread them, we like put them into 4 buckets, depending on the number of projects in instance, so that more or less equal number of instances are in each of the buckets. And the first thing that we compared was the average total utility that we have for all voters. And we kind of normalize it so that the utilitarian rule always have a utility of 1. So we can see that, for example, equal shares on average like scores between 80% to 85% of the average total utility of that of utilitarian, which is not very surprising because utilitarian is kind of greedy rule that just wants to maximize this value. So it's no surprising that proportional rule will score a bit lower than that. What is good to know is actually that both scores something in between both equal shares and utilitarian, and actually for small and middle size instances, this difference is significant. The second thing that we compared is exclusion ratio. So this is how many voters received 0 utility. So they didn't like anything that was selected in the end. So here it's the smaller the better. So for example, for large instances, equal shares is much better than utilitarian. And this is because it's just proportional rule. Yes, so it cares about these different groups of voters, while utilitarian really doesn't care. However, what is quite surprising is that for small instances, it's actually utilitarian that is better on average than equal shares. And how we can explain it? Well, it seems that this Halenka paradox is actually quite prevalent in, or like something that resembles this paradox, some kind of like this pattern is quite prevalent in the small instances. And this is why utilitarian actually can cover more voters with something than equal shares. So now it's very nice that actually BOSS is somewhere near the minimum of these 2 rules. So it's very robust in this sense. And the final thing we compared is how often EGR plus axiom is violated. So EGR plus is like very strong proportional axiom, even stronger, strictly stronger than EGR. And in very rough terms, it says that for every unselected project, there should be one of its supporters that has enough utility in the final selection. So we checked how often, for how many unselected projects on average it happens that there is no such voter. So for example, for utilitarian, it happens quite often. We have on average one such unselected project. For equal shares, there will be 0 because we can prove that it satisfies this axiom. And it's very good to know that for both, it actually happens very rarely. So there are some violations, but they are quite rare. So in practice, it's almost proportional. So to summarize, we introduced a new rule called BOSS bounded overspending equal shares. It solves the problems of equal standard method of equal shares. It works well in theory and also seems to work well in practice. So I think it's a good rule. Sorry, I think I overspent my time a bit, but I hope you excuse me for that. And thank you for listening.
Yeah, thanks a lot. So also a round of applause, please, to Tomasz. Okay, before we go on into the questions that are already in the chat about these different justified representation axioms, let me please also take the liberty as chairman to ask the first question, because it is, I mean, it's more general. How about computational complexity? I mean, even equal shares is not so easy, I assume, but this adds another layer of complexity, or does it?
So actually, all the rules that I was mentioning, they are polynomial, like run in polynomial time. And for equal shares, like basic equal shares and basic BOSS work in similar time. But for equal shares, sometimes you have to actually do a lot of more computation because of the completion methods. So in practice, actually, BOSS can be even faster than equal shares.
Oh, okay, interesting. So. Right, then I have a couple of questions here. So let me perhaps take on the EGR approximation question. What do you mean by EGR approximation? I think that would be a question to
okay, so the exact so the approximation is kind of in the sense also up to something. And this up to something, like we have some kind of parameter which depends on the, like, I don't want to maybe go into too much details, like it's described in the paper that is on arXiv now, but in like broad idea is that we look at the size of the group, because EGR basically, roughly speaking, for every group of given size, needs like every group of the given size is saying something and cohesive enough is said to deserve some amount of budget. And now what we are saying is that if the group is large enough, like maybe we will not give them the whole budget they deserve, but we will give them something. So there is something in this sense. I don't know, maybe if Piotr or somebody else wants to, in quick few words, say something more detailed about it.
If I can have, sorry.
Yes, we hear you. Please sign up.
Okay. So the point is, for BOSS, as Tomasz said, it's not optimal to satisfy EGR completely, such as Helenka paradox. But we say that, okay, for each group, such as S, we can guarantee EGR up to something, which means that we will not completely satisfy EGR, but we guarantee some amount of utility satisfaction, which goes higher by when the time S gets bigger. So when we talk about larger groups, they can actually control more part of the budget.
All right, okay, very good. Then a different question by Ariel. Ariel, you ask, why did you specifically choose rho divided by alpha as a criterion rather than, say, rho divided by alpha square or something else? I mean, some function. Yeah.
Okay. So the intuition is that we kind of say that, okay, you can pay more, you can overspend your budget, but now we will kind of give you utility from that, as if you would just buy a fraction of this project, while making you pay for the whole of it, and this will be your kind of raw. So you can so this is why we divide by alpha, because it kind of makes you decreases a bit your kind of this utility from what you get. And actually, it's inspired, like in the paper, we also analyze a fractional variant of equal shares, and it's kind of inspired by what we are doing in this. So fractional variant, where we kind of allow for buying a fraction of each project. And BOSS can be also thought of as kind of rounding up of some kind of rounding procedure of this fractional equal shares. So you kind of think about like, okay, maybe you can buy a fraction of this project, and then we kind of round it up. So you pay for it whole and only receive the fraction of the utility, and this will give you the raw that we are considering here, this kind of updated raw.
If I can quickly follow up, that makes sense. But I'm kind of wondering, in terms of the guarantees you get, for example, it's not clear that this choice would be better than, you know, as I mentioned, like rho over alpha squared or whatever, right? Maybe it gives you a better EJR approximation. Like, do we know anything concrete about?
Yeah, of course, we haven't yes, we only consider this one. Like, I'm not precluding that maybe some other will give better guarantees. I think it's very interesting research idea, but for future research. But I think it still works quite well with that choice. So I think, and that's good.
Thanks.
Okay, thanks for that question. I have. Wait a minute. The question: can you prove that BOS never exceeds the budget limit?
So actually, we kind of do it on the spot. So if we will never select, we just kind of prevent it from selecting project that actually goes beyond the true limit. So we don't, like, each round we only consider the projects that that at given round can still fit in the actual limit, actual budget that we have. So this is how we solve this. That's a good question.
Oh, okay. Then there is a question of Christoph. MES has a nice property that we were able to define money transfers from voters to projects. Now, some voters spend more money than B over N. Do we have some notion of money transfers now? How much more a voter may spend?
So I think we actually
understand the question.
Yeah, I think I understand.
Okay.
So we can we can just say that now we also have some money transfers from voters to projects, but just some voters spend more than their equal share. And I think we actually have some proof in the paper. Like, I'm quite certain that we have some proof in the paper that is bounded, that this overspending cannot be too much. Like it in extreme cases it can be quite substantial, but it cannot be unlimited. And this is why we can say that the overspending is bounded.
Bounded. Okay, I see.
But
all right.
If you could add to this question, but if there's one voter who approves a project that costs the whole budget, and no one approves anything else, BOSS would not fund this project?
No, okay. If nobody else approves anything, then BOSS will select this project. But I think like the bound comes into play where you also have other preferences. Okay,
yeah. Well, the bound is parameterized with the maximal cost in relation with the budget. So in particular, if there are like no large projects enough compared to the budget, then the bound is really small. And in the case where there are very large projects, then indeed it can be large, which is exactly illustrated by this example, and which is exactly intended.
I see.
All right. So any questions that I have not addressed by looking at the chat, please tell me now.
So you tested EJR plus because it's easy to check, but did you test experimentally also for EJR, maybe also for, maybe even just for small instances?
I think we haven't tested, but EJR plus implies EJR, so we have that. So we know that this happened only in 4% of
we
have some violations. So we know that only in this 4% can be also violations of EJR. But I think we haven't checked whether there is actually violations of EJR in all of these instances.
All right. So Sonja has the last suggestion, namely not to call it BOS equals shares, but simply BOS, and leave out the equal because it's not equal anyway. So and then and then it also doesn't coincide with the acronym of Boston Airport. All right. But anyway, okay. So yeah. Thank you. I think we're at the end of this session. So let me again thank the speakers of today for two very interesting and inspiring talks and presentations. I want to end with a remark that the general idea of this season of COMSOC video seminar is to have it on the last Wednesday of each month. But of course, this is only a general rule. It will not be followed exactly. But next time the seminar will take place is the 30th of October, which is the last Wednesday in October, and the speakers are yet to be announced. All right, so thank you, everybody, in particular the speakers, and I hope that we see again in approximately 1 month, a little bit more, on the 30th of October. All right, so bye-bye. Bye.